Two stagnant fluids are located in a long rectangular sections separated by walls. Assuming that the heat flux flows in only one direction as shown, that's upwards, how many thermal resistances would you use to determine the overall heat transfer coefficient for this problem? How many are conductive resistances and how many are convective resistances? Okay, so we have, this is the original drawing from the problem. I just drew it again here on the side for us to be able to see it better. So what happens? Let's first imagine, okay, that as you can see from that drawing on the left, let's imagine that our heat is starting from here, right, from the wall, as opposed to the surface. So if it's starting from the wall, as heat travels upwards, right, it's going to encounter a resistance, right? And we know that resistance, that's going to be a conductive resistance, right? So there'll be a conductive resistance, and that will be X K area. We know we calculated that plenty of times, where X is the distance that heat has to travel through that wall, right? Then what happens? Then the heat finds a barrier between a fluid and a solid. And we know that when there's an interaction between fluid and solid, or between two fluids, we're going to have a convective resistance, right? So right here, where these guys meet, there will be a convective resistance, or convective resistance, right? Then we know what happens, right? We know that this molecule, it's going to travel, this molecule will travel upwards according to difference in density, right? And then eventually it will find wall 2. When it finds wall 2, guess what happens? It's an interaction between liquid and a solid. So there's another convective resistance just there. Now, this convective resistance can be the same magnitude as the previous one, so long as the there's no change in whether the fluid is turbulent or not turbulent, if it's lamellar, and whether or not the K for wall, the material of wall 2 is the same material as wall 1, the roughness of wall 2 is the same roughness of wall 1. So most likely it will be different, but it can be the same magnitude. However, it's going to be a new convective resistance. Then the same story once again happens, right? Our heat is going to travel upwards, and do this in red. Our heat is going to travel upwards through this wall here, and we know it has to cover this distance here. We can call it Y now, and this distance Y will give us another resistance due to conduction, right? So that will be Y over K for the wall 2 times area. Then what happens? Same story, right? You see where I'm going with this. The same idea again. Boom, resistance when the heat finds the interface between fluid and solid. So that will give us a convective resistance just there. It travels upwards, goes there, and then boom, another convective resistance, like right there. Convective resistance right there. And once again, you can probably, don't have to tell this story once again, but then we're going to have a conductive resistance. And finally, last but not least, heat finds its way upwards from wall 3 to ambient. That's also an interaction between a solid and a fluid, which renders, guess what? Another convective resistance. Okay, so what does that leave us with? Let's count it down. 1, 2, 3, 4, 5, 6, 7, 8. So these 8, they have to be there. There's no other way. All right, these 8 have to be there for you guys, for you to get a correct answer on this question. Now, why could you argue more? Well, like some of you, the people who put 9 down, I would imagine, they put 9 down because they thought of the surface, right? Because if you look at this drawing here, you can see Q actually starts here in the bottom. So it would have to go through the surface, and that's why I drew the surface there. So we would have an extra conduction just here. According to this distance, it has to travel. So that will be a conductance there. If this is very, very thin, maybe we can ignore it, but regardless, you can argue that there will be a resistance through that surface. And then when we get to this point here, well, if it's a perfectly smooth contact, then fine. We won't have any barriers. It'll just go from one conductive resistance to the next one. But if we have any air pockets, any roughness, any air gaps like we studied before, we know there will be a resistance there, right here. And that will be the resistance of the gap, which is also related to a convective resistance, or you can think of it as the gap coefficient that we learned before, right? So that would bring us to a total of 10. So you could argue, and if this were an exam, and this wasn't an exam, you could argue this is 10 because of this and this and this, or you could argue this is 9, or you could argue this is 8, but the minimum is 8. How many of them due to conduction? 1, 2, 3 walls, right? To convection, 1, 2, 3, 4, 5 due to convection minimum. Right? So again, quick question to solve, but good question to get our heads around the theory, right? Around the theory that around the the thermal resistances. You guys have any questions?